Under this topic, we are going to talk about the inertia frames. So we are going to talk about the inertia frames of reference. So we see that inertia frames of reference, we looked at them in the previous video, we explained everything. When we say that, why is it that when you're standing in a moving truck and you throw a piece of chalk up like this, it will still come back in your hands? Why can't it go and fall back when the vehicle is moving? We looked at all those in our previous videos. So now we're going to look at the examples. So this is one of the example number one. So we are given that a particle of mass m moves along the ellipse. This and a force F. So if this is momentum, we are asked to prove that this B and C. So let's begin with part A. We are putting R times P because this. What you should know is that cross product is different from dot product. Those things are different. So cross product we always use the matrix determinant method. So back then, R times P, we are using matrix determinant method. So this is our I, J, and K. Now we go for the position breakdown. So position we have this. For I, we have this, which is A plus omega T, and J, we have this. And then K is not there. So we have a zero. Then P, what is our P? This P of ours is momentum. So we need to first find momentum. What is momentum? Momentum zero is given from M P. So now we need to find out that yeah. So momentum we get it from M P. So we are going to differentiate this to get velocity. So we can say that velocity is equal to the R dt, which will be equal to, now we are differentiating this position to get velocity. So it will be minus omega sine omega t I then plus b omega plus omega t j. Then our momentum will be minus m. So this is our momentum. Now this momentum, this is the I component and this is the J component. We can now put the back here. So I component, this one will be minus 8 m. So here there is an omega, and here there is also an omega. So it will be minus a omega, then m sine omega t, then h will be b omega m plus omega t. Then in the component it's not there. So we put the what? Put the zero. Then remember that we are proving the cross product of position and momentum is going to give us a zero. So now we are going to cross product. For I, we cross here, also cross here. So we get this multiplied by this, we subtract this times this, which is 0, and also 0. So 0I. So this is plus, this should be minus, and this should be plus. Then you go for J. J cross out this and this. Remember, this column and this column 0 minus 0. 0 is continue plus. Now, okay, we cross out this and this. This times this minus this times this. So it will be N B M omega cos squared omega t. Then minus now this, which is again minus A B M omega sin squared omega t is it that is. So okay here. So we can end up having this one becomes 0 plus. Here we can pull out the common factor. Common factors we have A, B, M, omega. So it will be plus A, B, M, omega into plus this becomes a plus. Okay. Hope you will be there. Then remember what we have looked at. We have looked at this back here. As you're proving, you keep seeing whether what you have is what is there. So our final answer this one is 1 from our trigonometric functions and relation. For part C, which is actually our last part, we are happy that we need to prove that so for part C, we need to prove the cross product of position and force is equal to 0. So what we shall do, already we have the position, then we know that force is equal to ma according to Newton's second law of motion. Then we can also get acceleration after differentiating twice the position. So once we differentiate the position, we get velocity, and once you differentiate velocity, you get acceleration. Then when you bring your acceleration and you substitute here, you get your force. Now you are having the position and force in terms of I and J components. So you can still use the matrix determinant method as we had done in part A, and you prove out to see if you have actually understood the determinant method of the matrix for cross multiplication.